Good morning, everyone. My name is Darssan Eswaramoorthi, and I'm honored to be presenting our work on SmartPilot, which is a multi-agent co-pilot for adaptive and intelligent manufacturing. This work lies at the intersection of agent-based AI, neurosymbolic reasoning, and manufacturing systems, aiming to bridge siloed AI competence with an integrated assistant for industrial settings. And we hope this work helps push vertical frontier for AI from research labs into the real world manufacturing plants. So in this presentation, I will be going over the background, main contributions, related work, core system framework, deployment setup of SmartPilot, results and evaluation, and conclusion and future work. So let's begin with the motivation behind SmartPilot. So in modern manufacturing, AI solutions tend to focus on isolated problems. You might have one system that detects anomalies, another one that forecasts production delays, and perhaps a third one that reasons over logs or documents. But these are typically just disjoint systems, and they don't communicate with each other or reason over shared context. This fragmented approach causes major blind spots within the plant. For example, a defect detection model may trigger alerts, but if it lacks causal reasoning, operators won't understand why the issue happened or how to prevent it in the future. Likewise, a predictive system may forecast delays but not explain them to the full context. So our proposal is SmartPilot, which is an agent-based copilot that addresses these limitations by holistically reasoning over time series data, causal dependencies, and other multimodal data and operators' knowledge. It is built to support real-time decision-making while being explainable, compact, and extensible. You can see a video demo of SmartPilot down there, and you can also, sorry. Okay, but yeah, the QR codes for the GitHub repository and demo video are right there. We can go over there if I have any time left in the end. So the main contributions of the paper that we cover are the development of SmartPilot, the innovative algorithms that we use, and multi-agent system design, the neurosymbolic methods, the enhanced explainability and comprehensive evaluation. First, we're introducing SmartPilot, um, multi, mul, modular multi-agent system for intelligent manufacturing. And we will discuss each agent which specializes in its own domain, such as anomaly prediction, causal reasoning, and document question and answering. But also this collaborates via the shared architecture, and I'll be going over that architecture. The second thing is the innovative algorithms we develop for each agent. These are lightweight models designed for real-time factory environments, integrating both neural and symbolic elements. Third, we implemented a multi-agent architecture that allows decentralized task execution while maintaining inter-agent memory synchronization. And then we show how we incorporated neurosymbolic AI methods, so the neural part and symbolic part, and to improve explainability without sacrificing performance. This hybridization lets us reason over events like if, let's say, a machine A has a lag and temperature is high, then failure probably increases, something pure deep learning would often struggle with. And then finally, we ran a comprehensive evaluation, including both quantitative benchmarks and qualitative expert reviews to ensure the system is practical and reliable in real-world manufacturing contexts. So we did explore some of the related work, and I'd like to go over that now. In the landscape of AI for manufacturing, this falls with traditional machine learning models that integrate narrow tasks. For example, XGBoost, as you may know, or DeepNets for defects detection or scheduling. However, they lack memory, contextual awareness, or generalization across multiple domains. Second, some efforts integrate knowledge graphs to improve interpretability and domain modeling, but they don't offer better structure, and they are rigid and it's hard to update over real time. And more recently, large language models like GPT-4 have been explored as general copilots, but these models lack structured memory and perform poorly in real-time, low latency environments and often hallucinate responses without verifiable backing because of the wide overkill amount of data that they get or they have available and they have to process through for each query. SmartPilot overcomes all of these limitations by combining the modular agents. It structures the neurosymbolic learning and real-time multimodal data processing, and it also bounds language generation and grounds its documents and events. So here's an overview of the SmartPilot framework. At the heart, we have this is the multi-agent structure that I've been talking about. And this consists four intelligent agents. We like to call them PredictX, Foresight, InfoGuide, and Causal Lens. In this presentation, I will mostly only be going over PredictX, Foresight, and InfoGuide, but Causal Lens is also under works right now. PredictX monitors data streams and predicts anomalies before they occur. Foresight models time-based dependencies and forecasts future production outcomes. And InfoGuide is a chatbot-style assistant that answers domain-specific questions grounded in manuals or logs that are available at the plants. And Causal Lens, just to give a rough idea, is mapping causal chains and discovers root cause of failures. These agents are not isolated. They interact, share intermediate outputs, and even cross-reference predictions. For example, PredictX can trigger Causal Lens when an anomaly is detected, and InfoGuide can provide corrective instructions grounded in historical context. The system also features a multimodal data integration, such as sensor data, images, and documentation, which are all fused in standardized internal schema. Finally, we have our neurosymbolic core, which enables agents to combine statistical learning with symbolic rules. This is key for explainability, which is critical in industrial AI applications where every detail matters. So this is an overview of the architecture that I'll be going over next. So this is how PredictX, InfoGuide, Foresight, and Causal Lens interact on a surface architecture level. Now we will take a look at the architecture of PredictX in a more closer way. So our intelligent anomaly prediction agent is designed for smart manufacturing systems. Unlike traditional monitoring systems that flag anomalies after they've occurred, PredictX looks ahead. It's trained to predict upcoming anomalies using a multimodal dataset composed of time series and image data, as you may see here, and which are then pre-processed respectively for the image stream. We focus on specific cycle states where anomalies are more likely to surface. Images are filtered, cropped, and passed through a zero-shot object detection pipeline. These images are then encoded using one of several modeling approaches: custom vision transformers and efficient net CNN, depending on the target use case and complexity. Meanwhile, the time series data is structured into sequential tensors that represent both the current and next predicted state of the system. These two modalities are then fused through a hybrid architecture and are passed through encoder-decoder models tuned for temporal forecasting. A unique aspect of PredictX is its integration with symbolic knowledge. Using a process ontology, the system brings in external domain rules that guide the neural model's attention. This means the model doesn't just output that an anomaly is incoming, but it also gives a deeper context of the event, whether it's caused by rising temperature, irregular torque patterns, or mechanical obstruction. The process ontology provides a layer of explainability by mapping model activations to interpretable process states. All of this flows into a fully connected layer that predicts the next time series step and anomaly label. So the output of this system would, in our use case, would be the anomaly label as well as when it could occur. These predictions are then surfaced to human operators via the InfoGuide agent, which I will also be going over in upcoming slides. And it presents both the alert and the reasoning behind it. By combining neural prediction with symbolic reasoning, PredictX helps operators not just react faster, but understand why a failure is about to happen, enabling faster, more confident interventions. So here is a use case that we've where we deployed PredictX. This was in our future factory system in McNair Aerospace Center in the University of South Carolina. So this use case demonstrates a rocket assembly prototype. Here, there's a robotic assembly line that constructs a rocket in 21 distinct stages along the conveyor belt. The process starts with the robotic arms sequentially placing four parts of the rocket: the base, the body 2, and then the nose cone at defined stations. These stages are captured as cell states, as we've explained in our paper, with key mechanical assembly events happening at states 4, 6, and 8. Multimodal data, in this case, is the pressure sensor readings and overhead camera images. This is collected at each state of the conveyor belt. This data is then passed to PredictX, which monitors for missing components. For example, let's say there's no pressure detected at base station 1 or base station 4, or if body parts are visually missing in the camera frame, PredictX flags an anomaly and it would say something like no body at 1 or no body 2. This then helps it predict ahead of time that the rocket won't complete successfully. based on partial assembly patterns and correlated sensor data. These alerts help operators intervene early rather than waiting for a full cycle to completely fail. This example highlights how PredictX fuses physical signals and image recognition to track real-world assembly tasks with precision, making it ideal for much larger manufacturing systems when trained. Now let's look at our second agent, which is Foresight. Foresight is designed to predict next hour demand in manufacturing environments using time series data. It operates using a stacked LSTM architecture, so long short-term memory architecture, which captures temporal patterns from continuous sensor streams. The main input is a sequence of timestamped features, for example, operational metrics or sensor readings over time. In addition to this, we include structured attributes, things like machine configuration, material type, or product line, pulled from external sources like the CSV files. And these are fed in as additional features and concatenated with the LSTM output just before the dense layer. Together, this fused representation allows Foresight to make a single-step prediction of demand for the upcoming hour, combining historical trends with contextual products as well as machine data. So now we'll take a look at a second use case where Foresight is successfully deployed. And this use case shows how it is in an industrial setting, specifically in Vegemite production in Swinburne University in Australia. The process begins with brewer's yeast. It's pumped into a storage, processed through multiple vats, separators, and eventually reduced to a concentrated paste using their triple effect evaporator. Foresight in this use case is used to predict the solid weight of each process sample. Solid weight is a key quality in this case for quality metric for determining product consistency. It uses time series data collected throughout the evaporation and separation stages, including variables like temperature, pressure, and duration. In addition, it leverages structured inputs like batch metadata, ingredient volumes, and operator settings, all which are concatenated as additional features as I previously showed in the architecture. And this is then used for the prediction. By forecasting the final solid weight early in the pipeline, Foresight helps operators make real-time adjustments to maintain uniform product quality, reducing waste and improving process control in this uniquely Australian food production line. So here is an architecture of our InfoGuide agent. This is our domain-specific system that supports decision-making on the production floor. InfoGuide just isn't a general-purpose chatbot. Instead, it is tightly integrated into the production prediction ecosystem, where a user query isn't just about real-time forecasting or anomaly detection. The system also invokes InfoGuide, which specializes in answering process-specific questions using internal PDFs like SOPs, user manuals, and summary logs. Technically speaking, InfoGuide operates using a retrieval augmented generation framework, so RAG framework. First, it retrieves the top K most relevant context passages from its knowledge base using BERT-based semantic search. These passages are chosen based on their similarity to the operator's query, which the user enters. Then, instead of relying entirely on a large language model, it uses a mixture-based model to generate a grounded response. And this hybrid approach minimizes hallucination, keeps outputs consistent with documentation, and ensures traceability by citing the source of every answer. Its architecture is therefore compact, modular, and efficient. This is built for edge deployment and low latency environments. What sets InfoGuide apart is its ability to connect the dots across multiple other agents. By grounding answers in both retrieved documents and agent outputs, InfoGuide becomes a super reliable teammate, not just another interface. It helps operators act with confidence, and it is also backed by real data and documentation. This is the complete deployment setup of SmartPilot, which is currently integrated into the Future Factories environment. At the heart of this setup is our PLC, or Programmable Logic Controller, which interfaces directly with factory components like the conveyor belts, robots, and sensors. This connection is established via OPC-UA, a secure industrial protocol used for real-time communication of analog sensor data. Camera inputs are also captured as visual data from the shop floor, and they are connected directly to the SmartPilot system, ensuring high-speed transfer for image-based analysis. SmartPilot also ingests structured textual data, including manuals, standard operating procedures, and logs. These are connected through a custom document handler built using Pylon, allowing SmartPilot to reference documentation during prediction and question and answering tasks. Once the data is ingested, SmartPilot integrates it with process ontologies and structured domain knowledge. This enables multiple downstream tasks, as we've gone over in the previous slides, such as prediction, production, interactive Q&A, and as well as causal discovery with root cause explanations, which is personalized to the user context. Altogether, this setup makes SmartPilot a unified reasoning layer that sits between raw machine data and human decision-making, delivering trustworthy, real-time insights in modern factory environments. This slide shows a demonstration of SmartPilot in action, highlighting both agent-level interfaces and a unified system interface. On the left, we see individual dashboards for PredictX and Foresight. You may also see a user explanation panel on PredictX. This view breaks down the alert by showing which sensor variables were responsible, what robot actions were occurring at that moment, and what the expected sensor values should have been. And we can also add more variables according to the user needs and the manufacturing plant's needs. This makes every prediction interpretable and actionable for operators on the floor. On the right, we have the system-wide SmartPilot interface, which invokes the InfoGuide agent. InfoGuide integrates outputs from all 4 of these agents and also connects them with the internal knowledge sources, like the manuals and logs that it has available. Users can also upload their own datasets, ask process-specific questions, and receive grounded responses, all within a single unified dashboard. So now let's take a look at the results that we collected, both quantitative and qualitative. PredictX achieved over 92% accuracy in an anomaly detection in the future factory cell, and this also avoided, this includes minimal false positives, using less than 15% of the memory footprint of traditional deep learning systems. So this demonstrates how our system was compact for a custom need. The average agent response time was under 1 second, making the system suitable for real-time shop floor interactions. Human operators evaluated InfoGuide's responses and rated them over 80% trustworthy, largely due to its citation, backed answers, and context relevance. Finally, in qualitative interviews, factory managers praised the system's explainability, especially the cause-effect mapping from causal lens and transparency of SmartPilot's decision paths. To wrap up, SmartPilot serves as a blueprint for vertical AI in manufacturing. It's adaptive, modular, and explainable, combining agents, symbolic logic, and large language model grounding into a single, efficient ecosystem. In future work, we plan to integrate active learning, where agents continuously adapt based on operator feedback. We also plan to develop human-in-the-loop interfaces that enable seamless oversight and override. Our end goal is to build a fully adaptive CoPilot that evolves with a factory. Ultimately, we envision SmartPilot evolving into a full-fledged CoPilot that understands, learns, and collaborates much like a human expert, but with machine scale speed and precision. We are a research team from the Artificial Intelligence Institute of South Carolina. I'd like to now thank our collaborators, Next Lab, Laboratories, Future Factories at McNair Aerospace Center. We'd also like to thank Clemson Composites, Bosch, and Swinburne University, as well as HPE. To view our demo video, please use that QR code, and our repository and wiki pages are available there as well. Thank you.